In the vast expanse of space, our Sun stands as our closest stellar neighbor, a mere 8 minutes away at the speed of light. Yet, despite its proximity and centuries of scientific inquiry, a fundamental question remains unanswered. What exactly is the Sun made of? This seemingly simple query has evolved into a complex scientific puzzle, challenging our understanding of stellar composition and the very fabric of the universe. The journey to unravel the Sun's composition began in earnest a century ago when most astronomers believed that the entire universe, including our star, was composed of the same elements found on Earth in similar proportions. This assumption was shattered by the groundbreaking work of Cecilia Payne, a Harvard graduate student in the 1920s. Payne's research revolutionized our understanding of stellar composition through her mastery of spectrography, the analysis of light spectra emitted by celestial bodies. Spectrography involves examining the patterns of light absorption and emission in stellar atmospheres. The Sun's spectrum, when observed closely, reveals a series of dark bands. These bands represent wavelengths of light absorbed by specific elements in the Sun's outer layers. Payne's meticulous analysis led to a startling conclusion. The Sun, and by extension, most stars in the universe, are predominantly composed of hydrogen and helium. All other elements, which astronomers collectively term metals, regardless of their physical properties, constitute a minuscule fraction of a star's mass. This discovery was paradigm-shifting. It revealed that the cosmos is primarily a realm of the two lightest elements, with heavier elements, including those essential for life as we know it, existing in trace amounts. The implications of this finding extend far beyond mere composition. The abundance of metals in stars provides crucial insights into the history of the universe, the formation of planets, and the potential for life elsewhere. Metals in stars are forged through nuclear fusion and dispersed into space when stars die. These elements become the building blocks for new stars, planets, and eventually life forms. Thus, determining the exact metallic content of our Sun is not just an exercise in stellar physics. It's a key to understanding our own origins and the possibilities for life throughout the cosmos. However, precisely quantifying the Sun's metallicity has proven to be an enduring challenge. The complexity arises from the nature of stellar spectra themselves. Different isotopes of the same element can produce varied spectral lines depending on factors such as temperature and ionization state. Moreover, spectral lines from different elements can overlap, making it difficult to discern individual contributions. To tackle this complexity, astronomers employ sophisticated models that attempt to match observed spectra with theoretical compositions. In 1989, a widely accepted model suggested that metals collectively constituted about 1.9% of the Sun's mass. This figure became the standard for nearly 2 decades, informing various aspects of astrophysical research and our understanding of stellar evolution. The established view was dramatically challenged in 2009 when a team of researchers published a new spectral analysis. This study, initially developed to examine ancient, metal-poor stars, employed more precise models with fewer approximations. When applied to our Sun, these refined techniques yielded a surprising result. The Sun's metallicity was significantly lower than previously thought, at only about 1.34%. This substantial reduction in estimated metal content had far-reaching implications. If our Sun contained fewer metals, it suggested that the rest of the universe might be less metal-rich than assumed. Given the critical role of metals in planet formation and the development of life, this finding potentially altered our expectations about the prevalence of habitable worlds and the likelihood of extraterrestrial life. However, the 2009 study's conclusions conflicted with another method of probing the Sun's composition: helioseismology. This technique, analogous to studying earthquakes to understand Earth's interior, uses vibrational waves traveling through the Sun to reveal its internal structure. Helioseismology has provided detailed insights into the Sun's layers, including the precise boundary between the radiative zone and the convective zone. The depth of this boundary is intrinsically linked to the Sun's metal content. Metals play a crucial role in making the Sun's outer layers opaque, which affects how energy is transported within the star. Helioseismological data places this boundary at 71.3% of the Sun's radius, a measurement that aligns with the higher metallicity estimates from earlier spectral analyses. The lower metallicity suggested by the 2009 study would imply a boundary closer to the Sun's surface, creating a significant discrepancy between spectral and seismic data. This conflict has sparked intense scientific debate and research. If the new spectral analysis is correct, it suggests our understanding of the Sun's interior may be flawed. Conversely, if the helioseismological data is accurate, it calls into question the new spectral models. The possibility that both our spectral and interior models require revision cannot be ruled out. In response to this puzzle, researchers have approached the problem from multiple angles. Some have refined spectral analyses further, leading to slight revisions in metallicity estimates. A 2021 update to the 2009 study, for instance, increased the overall metallicity estimate to 1.39%, still lower than traditional values but a step towards reconciliation. Other studies have produced different figures, such as a 2022 analysis suggesting a metallicity of about 1.6%. Parallel to these spectral investigations, scientists have been re-evaluating our understanding of the Sun's interior processes. A 2014 study focused on the properties of iron under conditions mimicking the Sun's interior revealed that iron is more opaque than previously thought. This finding suggests that even with a lower abundance, iron could have a more significant effect on the Sun's opacity, potentially explaining part of the discrepancy between spectral and seismic data. However, subsequent analyses of other elements' opacities have not provided such clear-cut results, instead raising new questions about experimental methodologies and interpretations. The ongoing research underscores the complexity of the problem and the interconnectedness of various aspects of solar physics. The quest to determine the Sun's exact composition highlights the dynamic nature of scientific inquiry. What began as a seemingly straightforward question has evolved into a multifaceted problem that touches on fundamental aspects of stellar physics, atomic theory, and observational techniques. The resolution of this puzzle has implications that extend far beyond our solar system, potentially reshaping our understanding of galactic evolution and the distribution of elements crucial for life throughout the universe. As astronomers continue to refine their models and observational techniques, the solar metallicity puzzle serves as a reminder of the challenges and excitement inherent in scientific discovery. It demonstrates that even our most familiar cosmic neighbor can hold profound mysteries, driving us to question our assumptions and push the boundaries of our knowledge. The ongoing debate surrounding the Sun's composition is not merely an academic exercise. It has practical implications for our understanding of stellar evolution, planet formation, and the potential for life in the universe. A more accurate determination of solar metallicity could lead to refined models of stellar structure and evolution, improving our ability to interpret observations of distant stars and galaxies. Moreover, resolving this puzzle could have significant implications for our search for exoplanets and potentially habitable worlds. The metal content of a star is closely tied to the likelihood and nature of planetary systems that may form around it. A better understanding of our Sun's composition could therefore inform our expectations and search strategies for Earth-like planets around other stars. As we continue to gaze at our Sun and ponder its mysteries, we are reminded of the interconnectedness of scientific disciplines and the power of collaborative research. The solar metallicity puzzle has brought together experts in spectroscopy, nuclear physics, stellar evolution, and computational modeling, fostering a rich interdisciplinary dialogue. In the end, the quest to determine the Sun's exact composition is more than a scientific challenge. It's a testament to human curiosity and perseverance. As we edge closer to a resolution, we not only enhance our understanding of our nearest star, but also gain deeper insights into the cosmic processes that have shaped our universe and our place within it.